We are waiting a couple more minutes. Audio should work. At least I hear Wojtek. Yeah. Okay, so people are mostly here, I think. Maybe Wojtek, could you start the intro? I think that around the time.
Oh, sorry, I was talking to muted mic. So, hello everyone. My name is Wojtek, and we are here on the 23rd Raz Wrocław. After a long summer break, we are back with the presentation from Bartek. But before that, I will just remind you who we are, what we are doing, and how can you help us. So let's begin. We are Raz Wrocław. We are the biggest Raz community in Poland. There are a couple of them in Poland, but we have the longest period of successful meetups. So thanks to you guys. Thanks to all the lecturers. And well, we have this very simple but important webpage, razwrocław.pl. You can find every possible link you need where you can find us, where we have discussions, links to our social media. So just remember that razwrocław.pl is what you need in most time. So as we said, we organized 22 meetings. We also organized one workshop and the Rusty Days Webference. You may recall us from July. And yeah, so we grew quite a big as for that niche language. We have our main sponsor, which is Anixa. Right now, because of the pandemic, we are not meeting offline in Python, but back then when everything was much simpler, Anixa was sponsoring our networking. So thanks to them. We have also a YouTube channel. You can, as I speak, we are streaming to it, so you can see everything hit here. There will be recording as well. So if you don't have time right now, don't you worry. We will just record it and send it to YouTube. And well, we are 4 people, 5 maybe, but as organizers, so we need your help. So if you wanna join our team, if you wanna have give a talk or just say something interesting about your project, or maybe you found something new about this new feature in the Rust, and you think this is pretty cool, or we think this is pretty cool as well. So don't be shy, share us. It doesn't have to be professional or anything like that. So don't you worry that you are not a lecturer, that you are not paid, but just be open, and we'll see you at the next meetup, I hope. And about past talks, we have also the GitHub. GitHub repository where we store all our, or most of them, our past talks, PDFs from the slides. So if you need something, mostly is that there's also a sub page for talk requests. So even if you don't feel like you can present, you can also make a request. So maybe you don't understand how borrow checker works. That's completely fine. You can request it. And then there are some people that they have knowledge about Rust and they are willing to share it, but they don't know which topic to choose. And that subpage will help them to make their decision. And well, the last thing is that we are just trying to be nice to each other. So this community is pretty small. We have no incidents here, and we would like to keep it that way. So that's it from my side, and let's give some applause to Bartek and his presentation.
Okay, just wait a second. Do you see my screen for now?
Yes, yes.
Okay, so hello, it's Bartek here from Wrocław, and today I will talk to you about real-life industry use case of failure with tower load balancing in the background. It is probably one of my shortest presentation with the longest title, so you know I needed to compensate the length of what I have to say. Who am I? I am co-organizer of this Raz Wrocław group and Raz Days conference from the May, I think. No, not May. Yeah, from the holidays. For now, I am Raz developer in Warsaw Stock Exchange since this month, so I don't work there for too long yet. Previously, I was working as Rust software developer in Luxoft and Anix. In Luxoft, I am still hanging out with my colleagues and doing some, let's say, consultations. I think that this cooperation to clarify, but it doesn't matter. And before I was into Rust, I was like committed C++ developer, but those times I think would never come back, or at least I hope. And simple disclaimer about this talk, as it is a real life industry example, there are some things I cannot talk about, and I would not go into details. I just want to show you the basic idea, what happened, why we default, and maybe it would help you not to fail in similar way in your, let's say, similar use case, or maybe it would give you some point of view on some things. Obviously, you can ask any question, but there's possibility that I would not be able to answer it. Okay, so the background. Basically, the project I was working on was 5G core network implementation, and 5G core network is just a set of microservices which are working in some kind of cloud, and the interfaces between those microservices are defined in some specifications, in particular using OpenAPI. So if you know something about OpenAPI, this basic it defines interfaces which are using HTTP requests with some JSONs in body, but with additional specific headers. So it's like three things. So headers, JSONs, and the endpoint address. It is not too much relevant to the talk, but this information about header is maybe important. Okay, so also there is this in the whole 5G core network. There's this very specialized element which is NRF. It is defined in some 3GPP technical specification. I pointed it out here, and it is basically the let's say DNS server for our setup for our microservices. In general, if you'd like to talk to another service, like for example to SMF, which is another well-defined service, you first need to ask NRF for any kind of current and ask him to which one you can connect with some queries, which I don't want to go into details. And with what is also important, it is possible that, for example, you have couple SMFs, and those SMF is one of the 5G services I mentioned before. They're indistinguishable from your point of view, so you basically can choose any of those you want. It doesn't matter which one you pick. One reason why it's this way is because you want to load balance across them. You even may have just one single service, but with like couple endpoints open, so you can maximize your throughput. And this was exactly the problem we needed to solve. So if we have indistinguishable endpoints, we want load balance between them, which seems to be a simple task, which is important in this case, that there is nothing like load balancing server, which would tell us which exact endpoint to use. We can just query NRF for a set of endpoints we can use, and we need to pick the one. What is also important, that the actual load balancing is not realized by choosing the actually different endpoint for performing the HTTP call. We are just setting a single specific header because there's additional proxy server which would always redirect the message, and we just need to fill the HTTP header to like pick the proper endpoint, let's say. So this is the problem, the problem background. And what is our idea? As our whole infrastructure is basically tower based, the first thought was just check what tower have for us. We just used Google or DuckDuckGo or whatever, and found that there is actually a crate tower balance which realizes load balancing. Yeah, so your problem is load balancing. There is a crate which realizes load balancing for your infrastructure. So, I mean, it's no brainer. Yeah, just pick it. Also, there is this tower balance crate requires from you to use additional tower discover crate, because tower balance is the thing which just picks the single endpoint, the single service from among what it gets, and how it gets the services. It just queries some kind of discover service to get knowledge. So I will show it in a while. So, but starting from the beginning, what is a tower? A tower is just like something like Hyper, maybe. I mean, Hyper is built on tower, but it is a framework for yeah, why not just hitting endpoints at random? It is basically one of the strategy, but there is pretty good paper from Nginx we actually considered, which proves that it is not always the best strategy. It doesn't gives you the best load balancing because it is not basically it's not guaranteed that your queries would be handled in the same amount of time. it is possible that, for example, you have couple 10% of your queries would be very long to handle, and if you would propagate your calls like equally, which should random do. Let's assume that random is pretty much good, and your distribution is like flat. But if this happens, then your 10% of queries might actually, fall into single or two services, and it's not the best situation. So there are another algorithms like power of two choices, which is just brought by Patryk Wychowaniec, and this is what is tower balancing using under the hood and what we choose to use, but it is not the only reason. I would talk about the only reasons why not to just pick random in a while. The other reasons are more like the specific problem reasons. But going back to the tower, what is tower? It's like a framework for preparing your I think TCP based, but I'm not sure if UDP is supported in tower, but basically request response services, like probably 90% of services on the market are just you send requests and you would like to have response, and this is such a common model that RAS provided this tower framework based on Tokyo, basically, which gives you this possibility to kind of and there is also a thing we are also using there, which is Hyper, which is even more specialized thing. It is just HTTP framework based on Tower. What is also important, that Tower is modeled as a stack. So you have like service wrapped into another service, wrapped into yet another service with kind of adapter decorator pattern. So you always have like this service and this chain of not of a chain of responsibility, I would say decorator, which are somehow modifying your request and then pass it to the underlying tower service to their thing. And when it reaches like something like hyper service, we just do the hyper call. Then it gives back the response, and the response is going back upway through the decorators, and it is also modified in like reverse order, let's say. I mean, could be modified because your service may obviously just forward to either request or response and modify only one of those. So this is basically how Tower is designed, and if you are building your applications using Tower, this is basically your applications architecture almost by force. So the main building block of Tower is this service thing, which basically has two functions, and the obvious function is call. We just perform call, yeah. So what you see here is you need pass request as your request as an argument. Request is something arbitrary. In our case, it is some fancy HTTP request, and then you have returned a future with an output of response. I simplified it a bit here, so there is not too much spam to look at. But in general, what is important is that the output of the future is the response type of service. Not even response time, but it is response or error, to be specific, I guess. I mean, those are details, yeah. And so call is basically the asynchronous call giving response for the future. But the important function here is pull ready. And why is this important? Because of how call is documented. Basically, the last sentence is very important, and it hit us hard, is that implementation should not take implementation of call never should take call poll-ready itself. And what is poll-ready? Poll-ready is a function which tells us if we can safely call the call method. So basically, if you are using the tower service, you cannot just call. Before you call, you need to do some kind of busy loop which would check what is returned by poll-ready, because it may either return an error. For example, if, I don't know, connection is broken or whatever, which means basically that your service is unusable anymore. You can have the pending result, which is not in this code, because I just took the most important part of documentation here, which means the service would be available later because maybe your buffer is overflowed and we are waiting till your buffer would be freed. And the poll may return ready, okay, which means, yeah, you can perform your call. And the tower infrastructure or tower utils even gives you utilities to allow you to call this, to not to implement this busy waiting loop on yourself. There is the ready structure which just does it for you. But the problem is that it is not obvious you need to use it. And someone who was like doing it for the first time in our project did not took attention to that. They did not have enough attention, so we never called the poll ready, and it worked. So why it worked is because under the hood of our whole tower stack, at the very end there was a hyper service, which is almost always ready. It is not ready only in case of buffer overflow, but unless you do any kind of stress test, you do not meet this case. And the problem is that if you call the call function when your poll ready doesn't return this okay, then your call may safely crash. It may safely panic, and it is correct behavior due to tower specification. So because the one who implemented tower in our stack first did not pay this attention, and he didn't do this poll ready call, then people were cloning and adding their own stuff, but without double checking the documentation, and it worked until we used the tower balance. I mean, as I said, hyper client is almost hyper service is almost always ready because it is nothing to wait for. It is not true before. It is not true according to the load balancer, because the load balancer does some preparation before call, and it does it in the poll ready call. So if we forget about this poll ready call and we just call, then everything crashes, and it is basically correct. So lesson learned: LTFM always, because it may save you troubles. So now going to our tower balance. So this is the main API of it. So there is this structure balance. It has a couple constructors. One of them is this from entropy. It would just use the OS random number generator. You can provide your own random number generator, and this is there are couple possibilities how to create this. And there is this service implementation. So for balance, the balance, the Tokyo balance is actually a tower service. And as you see, there is this discover thing, which is the tower discover type. I would go to it in a while. And now, what does it do? It basically performs two things. First of all, it before you call the call in full ready, basically, it takes it collects services it can use from Tower Discover. So Tower Discover is this crate which allows us to tell which services can we use and where we would like to do our call to the NRF probably. And then it picks the proper endpoint to call and picks the service to use. Yeah. Now the Tower Discover crate. I was talking. I mean the important thing here is the trait discover, which gives us the single service. But this is important how this service is done. Basically, there's this poll discover thing, which is another kind of poll-like function, which instead of giving you back the actual set of services you have available for you, it is like difference-based. You see that the result of this is the change of key and service. Key is some kind of key it would use for indexing your endpoints or services actually, because it doesn't need to be endpoints. It can be some more magic there. It's endpoint in our case. And on the other hand, you have this tower service which should be used to forward the call deeper in the stack. So as I said, this change, so you can either insert or remove previously added services to your stack, to your balancer. And this is a problem. This is a problem for us because in our case, before every call, we need to check in NRF what endpoints are available. But NRF doesn't tell us difference before current state and the previous call. It gives us the whole set of results. Yeah. So it is a problem. We need to adapt to that. And the other thing is that basically Tower Discover and Tower Balance as as consequence of that is service-based. So you don't just modify request for the load balancing or anything like that. You have another service for every endpoint you can balance on. So we need to implement additional layer, which is an endpoint. We need to instantiate it for every possible endpoint we can call to, and probably all of them would have common state, because under them there would be the actual hyper service with possible some additional things on stack, like wrapped in some kind of ars or something like this, because it's service which just modifies header and forward the call. It is as simple as that. And it looks like maybe not overhead, because we are in async world anyway, so overhead is not this big deal, but it's boilerplate. At this point, I was aware that our signal to noise ratio in our code is like not the best one, but we did our implementation. So we needed this service wrapper, which would just apply our header for the redirecting. This is very simple. It's okay. It's just, boilerplate, but doable. but there's a problem. We need to maintain our internal state, and it is not this simple thing. First of all, we need to keep the last response from NRF with in our some kind of state, let's say. It is simple as we can already pause our NRF responses, as we already had this implemented. We had working services, we just didn't load balance across them. So like say, keeping the result is just doing some shuffling around, but the next point is not this simple. I mean, you need to calculate the difference between current state and the previous state. And it is not simple at all. Calculating difference is never simple, because you need to like match the which endpoint from previous response is the endpoint from current response. You need to at least sort, sometimes do some more tricky things. I mean, it is a lot of work for CPU, for developer, and a lot of noise, because it is like, it's not rocket science, I would say, but it is this code you don't like to read. Maybe writing is not this bad, but maintaining this kind of thing is a pain. And Discover implementation is also another thing we probably need, but hopefully there is something which is called service stream, which just allows you to push your diffs to the Tokyo stream, or any kind of async stream. And this service stream would just have the receiver part of it, and would give those services applied to the stream to the balancer itself. So at least when we already calculated the diff, we just need to push all the changes to the stream, and this should work. And it basically worked with the problems. Like, as I said, signal to noise ratio was not the best. I mean, the overhead, the whole code base was basically the boilerplate for integrating with tower. The logic was like almost 1% or something like this. Any kind of improvements in terms of state maintenance, like we need to do additional to consider additional fields of NRF, or like influence the I don't know, availability of the services based on another like knowledge. This is something you don't want to do in your diff calculating code. I mean, in general, this boilerplate, which was related to state management, was not nice, let's say. I mean, yeah, and low-level control over load balancing strategy. We know it is in our head that it is not this simple. Like we just pick the power of two choices load balancing algorithm, because we know that the 3GPP specifications have additional additional cases when you, for example, limit the availability of a certain center service or whatever. We know at this point that we need fine-grained control about the instrumentation on which the load balancing could be performed. And there is a crate which is called tower load, which basically is meant for that. So you can integrate this with your load balancing and with your tower discover, and use it to add additional information about your service availability. But I mean, we already know how big boilerplate is to integrate with tower, and we would I mean, no, we didn't want to go for that, for integrating another tower puzzle to our our thing. And in this point, we realized that no way to continue with that, just because we've seen all those all those features we have in our backlog, which would be this difficult to integrate with our tower stack. So we needed to start from the scratch. So first thing, we needed to understand the algorithm. So this is the algorithm. I mean, I guess you already understand it. Just pick two things at random and take the one which is lower loaded. And according to Nginx article, it basically works. Now we need to keep some states as before, but now we have more control over this, how the state would look like. Yeah, because previously we had to use the different div-based state. Now there's nothing which would restrict us. We can do it as we want. So why we even need state? I mean, we need to keep information about how many, what is the load of our services. So basically, how many requests are pending responses for our endpoints, at least those endpoints which are used. So this is our state. I mean, this is simplification because we needed some logging and stuff like this. But in terms of business logic, we just need some hash map. And there is a double look on hash map because we sometimes need to create new endpoint, add new endpoint. So then we need to look for write. But in most cases, endpoints are just, we are using the same endpoints all the time. So in most cases, we just can log for it and increment or decrement the atomic counter. That's it. There is problem with state. I mean, it may grow infinitely, but this is another topic, and it can be handled some way. Yeah. So here's this drawback. So eternity with mistake, which which I just realized. But yeah, we can just implement the garbage collection on this, but we just need to check if this locking is worth that. I mean, it is not this common to lost endpoints, and endpoint is just a string. And the problem is that the question is that even worth it? Yeah. So also we need to, for our system, as our system is tower based, we need to look like a service. I mean, the thing we are returning from our which would perform the load balancing need to look like service. So we need to implement this. So we have already, which would just forward the call. We do not do anything which requires us for the lasting thing. So waiting, we implement everything in the call function. And what does this call function do? First, we need to perform an NRF query. We probably don't need to do this every time, but from the service point of view, we do it for every time. If we need to do some caching, then we exchange this NRF for cache, but it's irrelevant from this problem point of view. So we perform NRF query and extract the endpoints. Now we choose the endpoint using like suggested algorithm. We are creating the request counter in state, possibly write locking, but it's unlikely. We perform the call, so we just forward the call lower into the stack, into the tower stack. And when we got response, we just decrease the counter in the state. That's the whole implementation of call. It fits in, I think, 50 lines of code, something like this. I cannot present this because it's like NDA thing, but it's very short one, and it was super simple, and it worked. Like the whole implementation of the load balancing was lower than only diff calculation in the previous solution into heaven, and it was from this point of view it was perfect. state internals are trivial for now. If we need to like add any information about state, for example, we can keep information when to do the new NRF call, because, for example, we can use only cached data. For example, we can update new things to state, and it's super trivial for now. As algorithm is trivial and it is localized in one specific place, we can adjust it in any way we can, and it's very simple. We need to, for example, I don't know, retry with different candidates when the call fails. It's not a problem. It's in single place. We can do that. Also, we have less dependencies because we just get rid of 2 big crates, and we partially solved the polarity problem, which is not the real thing. I mean, we solved it because we don't have this tower balance, which needs to perform some preparations for call. But the problem have to be addressed anyway, because in future we can have like high load and it can come out. It's not that this is now proper behavior, but it's like delayed in time, and for now we can work with our features implementation. What is the outcome? In general, it worked. It was fast. It was easy to maintain, and probably because it is so simple and easy to modify, open for modification, it saved us so much work. For example, this additional load information I mentioned before are now very simple to add to the solution, and we do not need to like integrate another tower load crate to inject this information and add another boilerplate. And what's my conclusion for you is that there's this popular thing that programmers say, that do not reinvent the wheel. And it's not always that simple, because yeah, if you have very, very typical problem and you have no particular restrictions, then yeah, probably you need to use the like standard solution for that. But especially in cases when your specific problem has additional restrictions that you need to apply this change, and you have very, very many things you need to change in the starter solution, then it is very high probability that writing your own implementation from scratch may be beneficial, actually, especially when the problem is basically easy, simple one. Yeah. Obviously, I don't say that now you should write your HTTP server from scratch, because Hyper is bad or Rocket is bad, and no restrictions, then do not reinvent your well. But in case when your problem is simple and your constraints are, let's say, complicated, just consider it and measure if it would take you much time. And this is exactly what's my advice here. Any questions? Someone says that presentation doesn't work. I hope that's not true. I hope that Wojtek would mention it on VoiceCal. Okay, you don't need to ask questions relevant to the, related to the presentations. We can talk about any rusty things. Or Okay, I guess there are no questions, so I would just say thank you. You can find me mostly on Wrocław. This GitHub is just for curious people. I don't contribute too much. And yeah, that's all I prepared for now. And now we can talk about basically anything. If you